Okay, EEN 321. So this is part two of the video that we started on well, I guess Tuesday. And it's a continuation of chapter two on Coulomb's law and electric field intensity. So we said the last time that we looked again at uh, the force equation for electromagnetic forces. And we were reminded F is equal to QE plus QV cross B, E being electric field, B being magnetic field, Q being a charged material or particle, and V being the velocity or the motion velocity of the charged material or particle. We talked about the fact that for right now, we're going to ignore the magnetic field or just ignore the fact that we're going to restrict ourselves to the case where the charged material has zero velocity. So we'd be in the case where V would be equal to zero, and we can ignore the magnetic field portion of the equation and look primarily at the electric field. So this portion of our term is going to be zero for now, and we're going to look at this. We talked about the fact that the force is a vector, and in this particular case, the force is in the same direction as the electric field. And we could also see that in the case where you do have a magnetic field coupled with motion of our material, that the force is going to be perpendicular to the direction of motion as well as the magnetic field. Again, we're going to forget about that for now. So uh, next we kind of consider the fact that Coulomb, a French scientist, had done experiments and derived a relationship that he observed in terms of the forces between of attraction or repulsion between charged spheres. And he came up with this expression where the force is proportional to some constant K. It's inversely proportional to the square of the distance between the charged spheres, and it's also proportional to the magnitude of the charges on the two spheres. This K turned out to be 1 over 4 pi epsilon naught for the case of free space or air. And he derived what is the value of epsilon naught, 1 over 36 pi times 10 to the minus ninth farads per meter. And he calls this the Coulomb force. This is the expression for the Coulomb force. And by equating this to F is equal to Q times E, we kind of talked about this as the force on charge Q due to the electric field emanating because of charge one, or the force on charge one due to the electric field created by charge two. So from this, you can get an expression for the electric field, and we said that that was going to look like this. This is Q over 4 pi epsilon naught, 1 over distance squared from the location of your charge. So this is kind of what we talked about in the last lecture. Um, So today, what we're going to do is we're going to look at the case where the charges are no longer what we call point charges. They no longer are considered infinitesimally small uh, locations that from which we have an electric field being generated. And so I'm going to jump ahead in the lecture. And today we're going to talk about charge distributions. So previously, we talked about the case where the charged material was um, treated as a particle of infinitesimally small size and extent. But in real life and in many instances, the charged material is kind of smeared out. It has a distinct uh, extent in space. It can be linear, it can be a two-dimensional, or it can be a three-dimensional case. So these three cases, if you have your charge smeared out over a line, oh, excuse me, it's called a line charge distribution, or over a sheet or a surface, it's called a sheet or a surface distribution. Or the case where it's a extent is smeared out over a volume. In this case, it's called a volume charge distribution. And we will now look at how you figure out what is the total charge along this line or sheet or volume, and what is the electric field due to the charge smeared out over this line or sheet or volume. So when you compute the forces or the fields, Um, the first principle that you can think of as relevant to what we learned the other day is that even though the charge is smeared out over the one-dimensional, two-dimensional, or three-dimensional volume or extent, that there is sort of like a total amount, right? A total charge that's accumulated over this line or sheet or whatever. So if it's just distributed along a line, we think of the charge distribution as a line charge. It has units of coulombs per unit length. And in order to figure out how many total coulombs exist along this line, we integrate, and we call it rho sub L. Rho sub L dl will tell you how much is the total charge along this line. And if you know the total charge along this line, then we can kind of think about it as the same equations that we used previously, where it will be Q over 4 pi epsilon naught R squared if you're looking at what is the electric field from this line charge, or Q rho sub S, or the sheet charge, dA being a a differential for a two-dimensional surface. If you were working in Cartesian space, the two-dimensional surface would be dx dy, or dy dz, or dy dx, excuse me, dx dz, depending on which direction your surface is in. But anyway, it would just be dx dy. If it was a line charge, it would either be dx or dy or dl in Cartesian space. And then we have a volume charge density, rho sub v. It has units of coulombs per unit volume, and your dV would be your volume differential. So in Cartesian space, it would be dx dy dz. If you think about it in cylindrical space, we kind of went over this when we were talking about chapter one. It was rho d phi dz. And in spherical space, it was what is it, r squared sine theta dr d theta d phi, right? So um, these little differentials are either one-dimensional, two-dimensional, or three-dimensional, depending on if our charge distribution is a line charge, a surface charge, or a volume charge density. Okay. All right. So we're going to look at a couple of examples of how you get the total charge, and I kind of described it on the previous slide. Um, this is sort of like the theoretical equation. Actually, I don't like this equation, but it reminds me of, when I was taking calculus and they talk about, yeah, what we're doing is we're going to look at the change in one variable with respect to another. Um, under the case where the change approaches zero, the limit as the change approaches zero. But anyway, let's go straight to this one because this is the thing that I think is important. You're never going to look at this when you're solving problems. This is the equation that you're going to use. And I think I described it already, right? For example, for volume charge density, the total charge in the charge distribution is found by integrating over the volume. That the volume the line charge, excuse me, the volume charge density distribution is distributed over some volume, and if you integrate over the total volume, that gives you the total charge or the Q. If it's you're gonna look at the electric field due to that uh excuse me, volume charge distribution. If you're gonna look at the total Q, you do this integration, you get the total Q, and then this is the total Q that you have to use in your electric field equation. Okay. Um, all right, so here's an example. Find the charge contained within a 2 centimeter length of the electron beam shown in the figure. So this figure right here shows a portion of an electron beam. So notice that they're saying what is the total charge over a certain part of the electron beam, not the total beam. You can assume that if it's a beam, it doesn't just start and end. That's not how electron beams work. But for the purposes of this problem, they're saying, okay, if you just looked at a chunk of this beam along the z-axis for the value of it's a 2 centimeter length, right? It goes actually from z equals 2 centimeters up to z equals 4 centimeters. So that's the total length is 2 centimeters. It has cylindrical symmetry, like many beams do. It looks like a can, right, of some radius. And in order to find the total charge contained in this little chunk of the beam, we're going to integrate over the volume. But with one very interesting caveat, and that is the volume charge density, rho sub v, is defined not as some constant, but it's 5 e to the minus 10 to the fifth rho z. All right, so you got variables here in the expression for the volume charge density. All right, so you don't need to be, what's the word I'm looking for? Let's not get excited. In our previous examples, I say rho L, rho S, and rho V. Um, you don't necessarily have to have a uniform distribution. In the case of uniform, these numbers, rho L, rho S, or rho V, would be constant numbers, like 5, 5 coulombs per inch, or something like that, or 5 coulombs per millimeter, or 10 coulombs per meter squared, right? This is a uniform case. It's constant value all the time. That's not necessary. That's a special case. It doesn't have to exist. Here's a case where the volume charge density is in microcoulombs per meters cube, and the expression is uh proportional to how far you are away from the axis. That's what rho is. In a cylindrical system, rho is what is the radius of your circle, basically. So the radius of our circle in this volume goes from 0 out to 1 centimeter, right? After 1 centimeter, no more electron beam. But in the first 1 centimeter, you have a volume charge distribution. And it also is proportional to z. So depending on where you are along the z-axis, right, the volume charge density changes. But this is your expression for your rho sub v. So to find out the total charge along the volume, or within the volume, as described in the problem, we put in rho sub v times dv. Here's your rho sub v portion of your expression, right? Minus 5. Uh, well, where's this 10 to the minus 6? Oh, this might be a typo. Is it a typo? Yeah, it is. Right. So the rho sub v here should be minus 5 times 10 to the minus 6, e to the minus 10 to the fifth rho z. And that's what they have written here. Okay. So this is the rho sub v. And then the dv. What is your volume differential? Well, in cylindrical space or cylindrical coordinates is rho, d phi, dz. Okay. So now, the limits of our integration, they tell us the rho goes from 0 to 1 centimeter. So this part from 0 to 0.01. They're going to do this calculation in meters. So 1 centimeter is 0.01 meters. Okay. And then, oh, wait a minute. No, 1 centimeter. Yeah. 10, yeah, 0.01. Yeah, that's what 1 centimeter is. All right. And then the phi goes from 0 to 2 pi. You go all the way around, 0 to 2 pi. And then the z goes from 2 centimeters out to 4 centimeters. So 0.02 up to 0.04. Okay. So that's what they get here. And then now you just have to compute the integral, right? So hopefully this is not an integral that's beyond our abilities. And if it is, don't worry. By the end of the semester, it won't be. Okay. So you can look and see that the first thing they did is they said, okay, uh, our expression here has rho and z in it, but in terms of phi, right? There's nothing. So we're going to do that integral first. The 0 to 2 pi of d phi is just 2 pi. All right. So now, instead of minus 5 times 10 to the minus 6, now we have minus 10, okay, times 10 to the minus 6, which is minus 10 times 10 to the minus 5 times pi. All right. So they took this number and they multiplied it by 2 pi. And now we have to integrate over rho, and we have to integrate over z. All right. So, well, let's do that. Uh, so the next one the next thing I want you to do is I want you to recall. This is the integral that we have to do. But if you recall from your calculus course, and if you don't recall from your calculus course, that's okay. I think I mentioned in class last week that one of the best used books in my bookshelf is the math tables, where we can look up the integration or trig identities for very commonly used expressions. Turns out that the integral of e to the ax dx is 1 over a e to the ax. Okay, so where does this come in? Well, if you look at this, I want you to notice that we have e to the minus 10 to the fifth rho z, rho d phi dz. So you might recognize from here that this is very similar to e to the az dz or e to the a rho d phi rho d rho. All right, so we're gonna keep this in mind as we move forward here. So if I go to the next slide, you'll see that the author is suggesting, excuse me, that we should now do the integration over dz, so that the only thing we have left is the d rho. So if you take that formula from before and integrate over dz, we still have the 10 to the minus 5 pi, or minus 10 to the minus 5 pi. Then we have e to the minus 10 to the fifth rho and z. So if you look at this, you might be able to recognize that the A, this is the same as e to the AX. This right here is a constant, so it can come out front. But this little term right here is like e to the AX. But in our case, we're not using X, we're using Z, right? So the A part is minus 10 to the fifth rho, and the X part is Z, dZ. So we said that when you do that, it's 1 over A e to the AX. So 1 over A would be 1 over minus 10 to the fifth times rho. So minus 10 to the fifth times rho is in our denominator here. You still end up with e to the minus 10 to the fifth rho z. And then we still have rho d rho. And we evaluate from z equal to 0.02 up until z equal to 0.04. So when you apply those limits of integration, you have your z is here, you end up with this expression here. Okay, so we got 10 to the minus 5 in the numerator, minus 10 to the minus 10 to the fifth in the denominator. We have pi here. We have rho in the denominator. We have rho in the numerator. All right. So when you do that multiplication, you end up with this expression right here. And after you put in 0.02 and 0.04 for your z. So then you end up with this expression right here. And now we have to integrate over rho. Rho goes from 0 out to 1 centimeter, which is 0 to 0.01. Okay. So we're back to where we were before. This has the same form as e to the ax dx. Now our a is minus 2,000. In the second term, the a is minus 4,000. And our x is rho d phi, or d rho, excuse me. And in this case, we have rho d rho. So we can apply the same form for the integral to this term here and come up with a final answer. Okay. So when we do that, we end up with an expression that looks like this. Again, we say that our rho is going to go from 0 to 0.01. We plug that in, and we end up with a final term for our charge. Our total charge within this little volume is going to be 0.0785 picocoulombs. Okay, so I didn't actually plug these numbers into my calculator or into the Excel or something like that to make sure that they did it right. I'm gonna, say I'm sorry if there's some typo in here. But yeah, the point is this. Um, you just plug in whatever the value is for your charge distribution, and you plug in whatever is appropriate for your um, integration over either a line or a surface or a volume. Okay. All right. So as mentioned, the total charge was, or was it negative? It might have been negative. The total charge was, okay, it's going to be positive. The total charge is basically 0.0785 picocoulombs within the charge distribution. And so whatever, excuse me, the volume specified. So we might look at this as a 0.0785 picocoulomb point charge, but instead of being in a single point in space, it's spread out over a cylinder of size, height 2 centimeters and diameter 1 centimeter. Okay. Well, that's kind of the way we do that. So now, how does that play out if, we're not looking at what is the total charge, but we're looking at, how much is the electric field that's produced by that volume charge distribution? All right. So now, what we're going to do is for our electric field, this is kind of what we saw earlier, right? That our electric field is going to be the point charge divided by 4 pi epsilon naught r squared, where r is the distance from the point at which we're trying to evaluate our electric field to the point where the charge is located, all right? And the direction of the electric field is going to be along a vector uh, that goes from the uh, source charge to the point where we're trying to evaluate the field, okay? So when you have a distributed charge, unlike the case with a point charge, we just have a number or an expression for your charge. Now we have a smeared out charge. And in order to evaluate the electric field, in the same way that you had to do an integration to figure out what is the total charge, now we're going to have to do an integration to figure out what is the total electric field. And the limits of our integration is going to be dependent on, is the charge smeared out over a line, a surface, or a volume, right? If it's smeared out over a line, then we're going to integrate along the line where the charge is distributed. If it's over a surface, if the charge is smeared out over a surface, it's going to be over the surface, dA. And if it's over a volume, it's going to be across over the volume, dV. So, for example, in the case of a volume charge distribution, you're going to have an expression that looks something like this. Basically, you're going to integrate the little, you're going to integrate your rho sub v dv. That's the same as your q in the numerator. And you're going to have denominator is going to be 4 pi epsilon naught uh, distance squared. And that distance is the distance from the uh, source charge to the location where you're evaluating the field. All right, so notice we're evaluating the electric field at some place in Cartesian space or whatever, R. So R is got some value for X, Y, or Z. And the point charge, just I mean the charge distribution, the charge distribution. Ooh, it's late at night. It's late at night. What can I say? The charge distribution is over is located at some place R prime. All right, so it's going to be X prime, Y prime, Z prime. All right, so the charges are in the context of what we have in our textbook, the charges are going to be the primed coordinates, and the field point is the unprimed coordinates. So um, X prime, Y prime, Z prime, X, Y, Z. And the magnitude of the distance between the two, between the charge and the field point, is going to be r minus r prime, magnitude squared, right? Because it's distance squared. And then the unit vector is going to be r minus r prime divided by the magnitude of r minus r prime. Okay. All right. So in order to get the electric field, you would just integrate over the volume. So this dV prime, right? So you're integrating over the volume. Which volume is the volume where the charge is located? Okay, it's that volume. Okay. So if you're in Cartesian space, dV prime is dx dy dz. If you're in cylindrical, rho d phi, d phi, excuse me. And if you're in spherical, r squared, r now being the radius. This is not this, but r squared sine theta d phi. Uh r squared sine theta dr d phi d theta. Okay, yeah, yeah. It's late. What can I say? All right. So now the example. The example in the slide, however, tonight is a line charge distribution. Okay. So this line charge distribution, rho L, coulombs per meter, lies along the entire z-axis. All right, so this is the z-axis, and the rho L is along the z-axis. And you want to evaluate the electric field at some point P. The P lies on the y-axis in this particular case. So P has some value along the y-axis. It's going to be some value y. It doesn't have a z or an x coordinate. It's just y. Um, and the r minus r prime, well, the r is the distance from the origin to the field point, and the r prime is the distance from the origin to someplace on the line charge distribution. All right. So what we're actually doing is we're taking little chunks, d sub z, of our line charge distribution, and it's like, what's the distance from the little chunk d within d sub z to the point? So the r prime is going to be along this axis, but it's going to go from, well, from minus to infinity to plus infinity if it's the entire z-axis. So here's a special case where um, the little charge, the little portion of charge that we're going to look at is at some height z prime, because it's along the z-axis. It doesn't have a x or a y coordinate. The x is 0, the y is 0, but the z is equal to z prime. And when we do our limits of integration, because it's along the entire z-axis, it can go from minus infinity to plus infinity. Um, However, you may be able to see that there's symmetry in the sense that you have from 0 to plus infinity, and you have from 0 to minus infinity, right? So from 0 to plus infinity, you're going to have an electric field that's going to point like this. And from 0 to minus infinity, it's going to point like this. I should have drawn the, let's see, I think I can draw the line. It's going to point like, let's see, hold on. No, not a highlighter. Where's the one that says, no, I think draw. I think that's the one I want. It's going to do like, it's going to point like this. All right, so I can't draw straight. All right, I should have, there's another one. You know what? I think I can erase that. Erase. Erase. Come on. Erase. God dog it. How does this work? Eraser? All right. What I want to do is I want to draw a line. It's this one. Right. So the electric field is going to point in this direction for the DLs that go from 0 to minus infinity. Okay. So if you look at it and we're adding everything up, you can see that for every little element on this side, there's a equal and opposite on the other side. And when you add them all up, the components in the z direction are going to be as many going in this way as going down. So they're going to X each other out. They're going to cancel each other out. But in both cases, there's a component in the plus y direction. All right. So if I integrate from 0 to infinity, I can forget about the z component because it's going to cross itself out. But in the y direction, whatever I get, if I go from 0 to infinity, there's going to be another one from 0 to minus infinity that's going to be in the same direction. So it's like double, right? So I could go from 0 to infinity, multiply times 2, whatever I get in the y direction, and that's going to be my solution. I can forget about the z direction one. You might you might be able to see that. Hopefully you can see that. But anyway, I don't even know if I should have mentioned that. Maybe I shouldn't have mentioned it, but I did. Sometimes you can look at a problem and see that kind of infinity and make your final solution a little bit, what is the word? A little bit less difficult. Okay. All right. So anyway, our field point along the y-axis. So it's going to have some coordinate 0, y, 0, because the x and the z are 0. And our charge distribution is along the z-axis, so it's going to be 0, 0, z prime. And z prime can go from minus infinity to plus infinity, or you can do your integration from 0 to plus infinity and double the answer uh, for the portion that's going in the y direction. All right. Um, okay. All right. So if you were to do that, you would end up with an expression for your electric field. It's going to be an integration. You're going to integrate all of the little d sub e's. The d sub e's are due to the d sub q's, which are located um, uh, along the z-axis, and the d sub q's are equal to rho sub L dz prime. Rho sub L is your line density. It's in coulombs per meter. And the rho sub L could be a constant, a uniform line density, or your rho sub L could be it could be proportional to z. It could be 10 to the 10 to the fifth, excuse me, it could be e to the 10z or something like that. It doesn't matter. Just whatever it is, that's what you write into the equation. All right. All right. So um, let's look at how they did this. This is really interesting. Normally, I can use the little arrows to advance my slide, but I can't use the arrows when I'm in, what is this? Zoom. I can't use my arrows. I don't know what that's about. I think I have to get out of this tool thing. Now I can use my cursor. Yeah. All right. Okay. So, by the way, now that I look, I don't know how to notice this. They're doing this integration in cylindrical coordinates. So they're saying that our vector is going to be in terms of rho and a sub rho and a sub z. So the case that I gave you, which was Cartesian, z and y, the z directions are the same, but a sub rho, the rho direction is anything away from the origin, the z-axis, anything away from the z-axis. So um, the y direction is the same thing as the rho direction. Um, Basically, my phi is a constant. Um, anyway, so when we do this, you can go from minus infinity to plus infinity, and that's going to be dz prime, right? Dz prime, and the uh, the length of our little line charge element is rho dz. It's no, it's not. It's just plain old dz. What? Huh? Where did this rho come from in the denominator? Oh, okay. I know where it came from. Um, the rho comes from the vector r minus r prime. So this part right here is your vector, rho a rho minus z prime a z. So that's because this vector here is equal to r, and r is equal to rho, uh, a, a rho being the unit vector in the rho direction. And r prime is equal to z prime, and it's in the a sub z direction. So r minus r prime is rho a rho minus z prime a z. So you got rho sub L, that's your line charge density, dz prime, right? Because you have to a line charge, the charge is rho sub L dz prime. And the denominator, you have 4 pi epsilon naught, and the magnitude squared of your distance vector is going to be r squared, excuse me, rho squared. Rho being this, that's where the field point is being evaluated. Z prime squared, that's the height for your little uh, rho L dz prime. That's the height it is above the z axis to the 3/2. Okay, remember we talked about what is it? The magnitude is the square root of the component squared. And so when you cube it, you get to the 3/2. So that's what our dE is equal to. And we integrate over the entire z-axis from minus infinity to plus infinity. So when you do that, you end up with this expression here. All right, so here we got um, uh, this is our integral that we end up having to integrate. All right, so you may recognize what this is off the top of your head. If you don't, um, then you might need to use your what's the word? Your integral tables. That's probably what I would have to do. I would have to pull out my tables. Anyway, since you're integrating over on only over dz, um, the rho is actually a constant. There's no d rho. You're not integrating over rho. Rho is only one value. The rho value of rho is how far is your field point away from the z-axis. Excuse me. So you're this is a constant, and you got dz prime over some constant plus z prime squared quantity to the 3/2 power. And all of this part out here is a constant. So this comes out outside of your integral. And after you do your integral, this is what you get. And then you go from minus infinity to plus infinity. Okay. All right. So here's when you do this expression from minus infinity to plus infinity, you're going to end up with a value for your electric field. You'll find that your z component of the electric field is going to be 0, and your rho component is going to come out to be this. And here it is in terms of your vector. Okay. So if you go back um, to here, uh, I want you to notice you have an integration for the rho component, and you have an integration for the z component, right? So you're actually doing two integrals. Um, and if you did the two integrals, you would see that this integral turns out to be 0. And so you could do it that way. You could actually do the integral and show that it's going to be 0. Or if you look at the symmetry of the problem, you would be able to see that, okay, this is going to add up to 0. I'm just going to do this integral right here. But, you'd have to be able to recognize that. Be a good exercise if you want to actually do this integral and see that it's equal to 0. But I'm not going to make you do that. All right. So in this particular case, right, our line distribution was uniform. The value of rho sub L is the same all the way along the z-axis. In the previous example, we had a volume charge distribution, but it was not uniform. It varied with position and in specifics, it varied with the value of z, and it varied with the value of rho. Um, and in both cases, the examples that the author uses in the presentation is a cylindrical coordinates integration. All right, so there's another example here. I'm not going to go over it in this video, but this is an example where the line distribution is not on the z-axis, right? It's at some position. It's in the direction of the z-axis, but it's at some position where it's located off of the z-axis, right? And in this particular case, um, it's located with the x equal to 6 and the y equal to 8. All right, so again, uh, they have two positions? Yeah, they have two positions that they're looking at. One is a position XYZ, and the other, no. This is just one position. Okay, so with the line displaced to 6, 8, the field becomes. Okay. All right. So what they're showing here is, yeah, I'm sorry. What they're showing here is if you look at the expression here, this is for the case where the line charge distribution is located along the axis, the z-axis. But you can quickly, what's the word I'm looking for? You can quickly use uh, the conversion. The conversion between cylindrical and Cartesian coordinates to find out what the distribution is going to look like when you're not at the z-axis, but at some axis along the z direction located at 6, 8, right? And to do that, you have to notice that the rho is always equal to the square root of x squared plus y squared, right? If you want to do it that way, you'd have to notice that the rho is equal to x squared plus y squared. And so if you realize that, um, uh, in one case, your x and the square root of x squared plus y squared. In one case, the x squared, the x and the y is equal to 0. But now you're moving things, and so your vector is x minus 6 and y minus 8 because you're located at 6 and 8 and in the z direction. So the expression is easy is kind of easy to make the conversion, but you have to know how to convert between Cartesian and cylindrical coordinates. And it's also that you need to understand that um, your vector direction, right, is going to be related to um, a conversion between a sub rho and a sub x and a sub y and a sub z. But they have kind of looked at this as understanding that it's going to be in the direction away from the axis, so to speak. And so you need to understand that this is going to depend on where your field point is. And so in order to know what this A sub R is, you have to know a little bit more about where your field point is. Um, so that's kind of another example for how you can use math and vector manipulations in order to make something that's a little bit more difficult and a little bit more complicated easy. Just take the axis or the distribution, translate it to the z-axis, get your solution, and then translate the solution back. I don't know that I'm going to give you any problems like that, but that's kind of one of the things that you can do if you become what's the word I want to use? Comfortable with manipulating vectors. And so this is the kind of problem that I probably would only give you in a homework problem. I wouldn't give it to you on a test. Uh, Um, okay. All right. So um, there's a final example. I'm not going to go over this tonight either, where you look at a sheet charge. And so a sheet charge is in two dimensions, right? Dx, dy, or, depending on where you are on the surface, it could be on the surface of a can. Then that would be, what is that? Rho d theta, uh, yeah, rho d theta dz, um, or on the surface of uh, a sphere, uh, r squared sine theta d theta d phi, right? So it depends on what kind of surface you're looking at and what the ds looks like. So, um, all right, so I'm gonna stop here. There are a couple of slides at the very end where it talks about streamlines. I'm not gonna cover that in this particular chapter. All right. So, yep, I'm only showing my avatar because it's nighttime and you shouldn't see, what I'm looking like right now because I'm tired. I hope all is well for you. I will be back on Tuesday, September the 10th, and I'm going to put up an announcement. By the way, we have a speaker coming in on Tuesday from Sandia, and the presentation, I believe, is going to be at 5 o'clock on Tuesday, September the 10th. And she's going to talk to you about how to apply for internships. So the Sandia internship I consider to be highly competitive. It's one that I would like for us to have a lot more students participating in this program. It gives you an inside track to a job offer from a national laboratory that does outstanding work in areas of energy and or microelectronics. Um, and I'm gonna, give a strong encouragement. In fact, I'm gonna do some kind of a bonus, right, if you go. I apologize that I can't to give you much more specific than that tonight, because my life is too busy. But there will be an announcement. Here's what I really want to say. Save the date. Tuesday, September the 10th, 5 o'clock. I believe it's in RTC 136. Presentation is going to be something like maybe 60 minutes. Um, and again, there'll be some basic information on how to apply for internships at Sandia National Labs. This is a highly competitive program, and I think you have to get your applications in something like in November, right? Because they have to choose you and go through some kind of what's the word I want to hear use here? Approval process. You have to get a clearance. That's it. You have to get a clearance to go out there and work for them. You could be at Stanford, or you could be in Albuquerque, or you could be at Oak Ridge, or you could be at Fermi Labs in Chicago. It's not clear, you could be at any one of these places. I think they also have a lab out at Brookhaven in New York, Long Island, New York. So any of these places, you could get an internship at any one of them, and I want you guys to get them. So save the date. All right, that concludes the recording for tonight. I hope you have a nice weekend, and I'll see you next week.